Welcome to section 7.4. In this section, we're going to talk about how we're going to integrate rational functions. And the method that we're going to develop here, which is called partial fractions, is a very powerful technique that will apply actually to any rational function, although the sorts of rational functions we can do by hand in practice is somewhat limited. There will also be notes that I post on how to use a computer to do this method for problems that are more complicated than those that you'll do by hand. The first thing that we should remember is what a rational function is. So if I say f of x is rational, the first thing you should think is fraction. But a rational function is more special than just a function that has a numerator and a denominator. It's a fraction of polynomials. So remember that a polynomial is a function of the form p of x is equal to an x to the n plus an minus 1 x to the n minus 1 plus a1x plus a naught, where an through a naught are constants. And usually we think of an, the leading coefficient, as being not equal to 0. So with that, we can say that the degree of a polynomial is equal to n. That is the power of the leading term. F is rational if f of x is equal to p of x over q of x for p and q polynomials. The technique of partial fractions applies to rational functions that are what are called proper. So a proper rational function is one where the degree of the numerator is strictly less than the degree of the denominator. F is a proper rational function if f of x is equal to p of x over q of x, where p and q are polynomials, and the degree of p is strictly less than the degree of q. So as examples here, f of x is equal to x squared plus 1 over x to the third plus x plus 1. That's a proper rational function, because the degree of the numerator is 2 because its highest power is 2, and the degree of the denominator is 3 because its highest power is 3. The technique that we want to use only works on proper rational functions, and that means that we're going to have to remember how polynomial long division works, because any improper rational function can be turned into a proper one by division. Any rational function that is not proper can be written f of x is p of x over q of x, and then you can do division to write it as some regular old polynomial s of x plus r of x over q of x, where this is a polynomial and this is a proper rational function. For many of you, polynomial long division is something you haven't seen for years, and even if you did see it, you probably didn't particularly care for it. So I'm going to remind you how it works. Let's look at, say, something like x to the third plus x plus 1 over x squared plus 1. Now this is a rational function because the numerator is a polynomial and so is the denominator. And it's not a proper rational function because the degree of the numerator, the degree of p, is 3, but the degree of the denominator is 2. So it's not proper. The way that we're going to make it proper is we're going to use long division. After all, what does this fraction represent? A fraction represents a division problem. And the division problem that it represents is x squared plus 1 divided into the polynomial x to the third plus 0x squared plus x plus 1, where I have to make sure that I have a spot for every power of x inside the polynomial here. Now, Some of you may have learned synthetic division in the past. We're not going to be doing synthetic division here largely because most of the polynomials that we're going to be dividing aren't to the first power down here. So it's not going to be worth taking the time to go over synthetic division, which is a special case of polynomial long division. So how do we do it? Well, we're looking for a number that we can put here that when I multiply x squared times whatever goes there, I get x to the third so I can cancel it. So the question you're asking yourself is, x squared times what? X squared times what is equal to x to the third? And the answer is x. Then you take x and you multiply it by everything over here, and you put the result in the proper columns of the division problem. X times x squared is x to the third, and x times 1 is x. And just like a regular division problem, now you subtract. X to the third minus x to the third is 0. 0x squared minus 0x squared is 0. X minus x is 0. And 1 minus 0 is 1. Now this thing right here is of lower degree than what we started with. So there's nothing that I'm going to be able to multiply x squared by in order to get a 1. Right? No polynomial times x squared is equal to 1. Since I can't find a polynomial that does that, I'm finished, and this is called the remainder. So now we have all the pieces that we need to construct our polynomial plus proper rational function. The polynomial is whatever you get here, the quotient. So x. So this entire expression is equal to x, which is the polynomial that we got as our quotient, plus the proper rational function that we get by taking the remainder and dividing by the divisor. This is what we call the reduction of x to the third plus x plus 1 over x squared plus 1. Taking a rational function and putting it into a proper form you can think of as a reduction. So once we have a proper rational function, what can we do? It turns out that there's only 4 kinds of proper rational functions, and the method of proper fractions can be used on all of them. But the cases differ, and so we're going to go through them one at a time. In all of the examples that we're going to be doing, we're going to assume that f of x is a proper rational function, and that q of x is the denominator. That is, I'm thinking f is equal to p divided by. So why are there 4 cases? A theorem called the fundamental theorem of algebra says that any polynomial can be factored into products of linear terms and irreducible quadratic terms. What do I mean by that? So a linear term is a term that looks like ax plus b. Looks like a line, mx plus b. Okay? An irreducible quadratic is going to be of the form ax squared plus bx plus c with the additional condition that b squared minus 4ac is negative. Remember, this quantity is called the discriminant. And if the discriminant was negative, it means that in order to factor this, I have to use complex numbers. So we're not going to use complex numbers in this class. And that means that we're going to consider something like this to be unfactorable over the real numbers. There's no way that I can take this and break it into smaller factors without using the complex numbers. And a striking fact is that every polynomial can be factored into piles of stuff that looks like this. So for example, if you wrote something like x to the third minus 1 down, and you get x minus 1 times x squared plus x plus 1, this term is linear because it's to the power 1, and this term is an irreducible quadratic, which means I can't factor it any further. And the reason that you know you can't factor it any further is because if you check, you could get 1 squared minus 4 times 1 times 1, which is negative 3. That means that the discriminant of this is 0. It will only factor with complex numbers, and so it's irreducible. Now the question of how to get the factors is more complicated. So we're not going to be able to do super crazy examples here because we're going to need to be able to factor the polynomials that we're going to use to create our examples. So the cases that we're going to talk about refer to the possible ways that Q factors. The first case is that Q of x is a product of distinct, by which I mean they're all different, linear factors. As an example here, something like 1 over x plus 1 times x plus 2. This is a rational function that has two linear terms, and you can tell that the terms are different, so it is a product of distinct linear factors in the denominator. And this only applies to the denominator. Okay. As another example, something like x squared plus 1 over x plus 1, x minus 1, x minus 3. The denominator is a product of distinct linear factors. The idea of partial fractions is that any rational function can be broken up into very simple fractions, and the simple fractions that you get are easy to integrate. In this case, what the partial fraction theorem says is that if you have a q of x, which is equal to a1x plus b1, a2x plus b2, akx plus bk, that is, we have k distinct linear factors that q factors into, then f of x is going to turn out to be able to be written as a1 over a1x plus b1 plus a2 over a2x plus b2 down to akx plus bk. And the reason we call these partial fractions is because each one of these is a partial fraction. So these are the partial fractions. The important thing here is the a1 through ak's are constants. All of these are constant. And so that means if I could find a1 through ak, then I'd have a way of writing f down where I know the integral of all the pieces it breaks into. The integral of each one of these is a logarithm and a logarithm and a logarithm and a logarithm and a logarithm all the way down the chain. So any rational function that has the property that its denominator factors into these linear terms can be broken up into pieces that integrate into logs. So what does that look like in practice? Let's do an example. Let's look at the integral of 1 over x plus 1 times x minus 2. Now with a quadratic like this, there's probably other approaches we could take. We could FOIL this out and use completing the square to try to write it as some kind of difference of squares, so we could use inverse trig substitution. But let's try to deal with this with partial fractions instead. So the partial fraction step is to say, well, I have these distinct linear terms in the denominator of the fraction. And what the partial fraction theorem says is that I can break this up into a fraction that corresponds to x plus 1 and a different fraction that corresponds to x minus 2, where the a and the b are unknowns. If I could find them, then I could just put this easy function up inside the integral and integrate this into a log and this into a log. How do I do that? So the typical trick is we think of taking the entire equation and multiplying by the denominator of the left-hand side. So I'm going to take everything and multiply it by x plus 1, x minus 2. On the left-hand side, the denominator clears completely. 1. On the right-hand side, what will happen is when you take this and multiply it by this term, the x plus 1's cancel, and what you get left over is a times x minus 2. Likewise, when you take b over x minus 2, when you multiply it by something that has an x minus 2 on top, is the x minus 2's cancel, and what's left over is the x plus 1. From here, there's two approaches you can take. The first approach is to multiply everything out and then use a comparison of polynomials to figure out what a and b must have been. If you do that, what you're going to get is a plus bx plus negative 2a plus b on the right-hand side. Now, polynomials are only equal if the coefficients of their corresponding terms are equal. And what I mean by that is the constant term on the right-hand side is a 1, and the constant term on the other right-hand side is negative 2a plus b. And that means in order for these polynomials to be equal, those constant terms have to be equal. So you get out an equation. 1 is equal to minus 2a plus b. Also, there's an x term on this side, and the x term has coefficient a plus b. There's a 0x on this side, and so that means that the 0, that's the coefficient of the x squared on the left side, has to be equal to the a plus b, that's the coefficient of the x term on the right-hand side. This is a system of equations that you can solve for a and b using methods that you learned in pre-calculus, for example, elimination. So I could subtract the second equation from the first, and I'd end up with 1 is equal to minus 3a. And that means that a is equal to minus a third. And since a and b add to 0, that means b must be positive 1/3. So to do this, you use ideas from systems of equations. And right here, you should see where the difficulty is going to be. Systems of equations get actually difficult to solve as the number of variables goes up. So this is a 2x2 system. It's very easy. But if there had been 3 terms over here, there would be 3 coefficients to solve for. We've shown that 1 over x plus 1 times x minus 2 dx can be written as the integral of negative 1/3 over x plus 1 plus 1/3 over x minus 2. To get from here to here, that is what we did with partial fractions. So the partial fraction step is what we did right here, where we took this rational expression and we broke it up into its partial fraction pieces and then solved for the coefficients. Once we have the partial fraction decomposition, we can take the integral and we can replace this thing I don't know how to integrate with this thing that I do, because this is equal to minus 1/3 times the natural log of x plus 1 plus 1/3 times the natural log of x minus 2. And at this point, you're finished. In case 2, we assume that q of x factors into linear factors, but that some of those might repeat. So by repetition, I mean if q of x was equal to something like x plus 1 squared times x minus 1, this is a repeated term. So case 2 is going to be q of x factors into linear terms with some repeated. So we have to modify how we use partial fractions to account for the repetition. The way that we do that is, for each copy of the repeated power, we get a different fraction with that denominator. So what I mean by that is, if q of x had a term that was a1x plus b1, and that was repeated r times, then the way that you would write that would be, when you wrote f down, then when you wrote f down, what you would have is one partial fraction corresponding to the first power of the repetition, and another partial fraction corresponding to the second power of the repetition, and another partial fraction corresponding to the third power of the repetition, where we're increasing the power of the denominator from 1 all the way up to the ending fraction, which is a rx plus br to the rth power. So when you get to the end, the power here should match the power here. Now that might look confusing. Let me show you what it looks like in practice. It's not so bad. So let's see if we can write down the partial fraction decomposition for f of x is equal to 1 over x plus 1 to the second times x minus 2 to the third. The idea here is that I'm going to get partial fractions that correspond to both the x plus 1 term and the x minus 2 term. And because I have repetition here, there are going to be 2 fractions that correspond to the x plus 1 and 3 fractions that correspond to the x minus 2. But those denominators have to be different, or really I haven't written down 3 different fractions. So a over x plus 1 plus b over x plus 1 squared to account for the 2 fractions we need for the 2 repetitions, plus c over x minus 2 plus d over x minus 2 squared plus e over x minus 2 to the third. 1, 2, 3 copies based on the power of the repetition. Now, I'm not going to go through finding a, b, c, d, and e in this example. I want to work on a more practical example, but you can imagine that the approach to this would be exactly the same. You would take the left-hand side with the 1 on the numerator and the right-hand side, and you would multiply through by the entire denominator, and you would end up with this enormous polynomial expression in a, b, c, d, and e. And you'd have a 5x5 system of equations you'd have to solve in order to find those coefficients. I promise when we get to the end, I will show you a more efficient way of doing that for very complicated problems. Let's look at the integral of x minus 1 over x plus 1 times x minus 2 squared dx. In order to integrate this, I'm going to have to decompose the fraction first. So the very first thing I'm going to do is the partial fraction step. And the partial fraction step says that x minus 1 over x plus 1 times x minus 2 squared should decompose into 3 fractions: a over x plus 1, b over x minus 2, and c over x minus 2 squared. 1 fraction for the x plus 1, 1 fraction for the first power of x minus 2, 1 fraction for the second power of x minus 2. You can always predict the number of fractions there are going to be because there's 3 repeated linear terms down here. That is, the degree of the denominator is 3, and there's 3 fractions to go with it. So every time I have a linear term, I have a partial fraction that goes with it. So how do I find a, b, and c? Well, multiply through by the denominator, and what you're going to get is, so if you take all of it and multiply through by x plus 1 times x minus 2 squared, then what you're going to end up with is an x minus 1 on the left-hand side, and on the right-hand side, a times x minus 2 squared plus b times x plus 1 times x minus 2 plus c times x plus 1 because of cancellation. Now, in order to find a system of equations that goes with this, I'm going to have to multiply all this out and collect like terms. Remember, I'm only working on the right-hand side. The left-hand side is going to get left alone because that's the basis for my comparison. So how many x squareds do I have floating around? Well, let's see. This is x squared minus 4x plus 4 plus b times x squared minus x minus 2 plus c times x plus 1. So I'm looking for things that have x squareds in them. Well, there's an ax squared and a bx squared, but no c's. I see a negative 4a that's stuck onto an x right here. I see a minus b that's stuck onto an x right here. And I see a positive c that's stuck onto that x. And finally, the constant terms are going to be, there's a 4a, there's a minus 2b, and there's a plus c. As you can tell, partial fraction problems also tend to be algebraically lengthy. So now I'm going to try to find a, b, and c, and I'm going to do it by setting up a system of equations. There is no x squared term on the left-hand side. So I'm going to say, well, the coefficient on the right-hand side then must be 0. A plus b must be equal to 0. There's a 1 as a coefficient of the x on the left-hand side, and there's this thing as a coefficient of the x on the right-hand side, and that must mean that minus 4a minus b plus c is equal to 1. And finally, the constant term on this side is 4a minus 2b plus c, and the constant term over here is negative 1. So that must mean that 4a minus 2b plus c is negative 1. And here we have a system of equations that we can break down. If you don't remember how these tend to go, I'm going to walk through this example of solving a system. We're going to combine the second 2 equations together in a way that eliminates the c, because that will leave us with an equation in just a and b. If I do that, what I get is, okay, so if I multiply this equation through by negative 1, what I get is minus 4a plus 2b minus c is equal to 1. And I wanted to add that to the equation minus 4a minus b minus c is equal to 1. And if I add, what I end up with is, that's not where the minus goes, I missed a plus. If I add, I'm going to get minus 8a plus b is equal to 2. Now I have this equation. I've combined these two together to get this equation, and I've got a new system that's smaller. A plus b is equal to 0, minus 8a plus b is equal to 2. I can subtract again, and what I'll end up with is 9a is equal to negative 2. So a is minus 2/9. But a plus b is equal to 0, which must mean that b is equal to positive 2/9. Once I know a and b, I can go back and figure out what c must have been. So I can use any equation I want. Let's just pick this one for the sake of argument. That means that minus 4 times negative 2/9 minus 2/9 plus c is equal to 1. So I get 8/9 minus 2/9 plus c is equal to 1. This is 6/9. If I subtract from both sides, I get c is equal to 1/3. So we started with the integral of x minus 1 over x plus 1 times x minus 2 squared dx. And what we've shown is that I could rewrite this as the integral of minus 2/9 over x plus 1 plus 2/9 over x minus 2 plus 1/3 over x minus 2 squared. And I have a technique for each one of these. I see natural logs here, and then I also see a regular old u substitution. Using techniques that we've developed over the last 2 chapters, it's very straightforward to see that this integral is minus 2/9 of the natural log of x plus 1. That's just a regular old u substitution. Plus 2/9 of the natural log of x minus 2. That's a u substitution. And then using a u substitution and the fact that the integral of u to the minus 2 is minus u to the minus 1, we can write minus 1/3 times 1 over x minus 2. And there's the answer. Case 3